Stokes' theorem, it relates the line integral around a closed loop, the boundary of a surface, to a surface integral over the surface bounded by that loop. So the closed line integral is equal to the curl of the function over the surface. So let's say f is our usual y x unit plus z y unit plus x z unit. Let's say our surface is the plane x plus y plus z equal to 1. So the boundary curve, so this is going to be in the first octant. Let's say x, y, z are all greater than or equal to 0. The boundary curve formed by intersections of x plus y plus z is equal to 1. So the first step would be to parameterize the boundary curve. So we have the points 1, 0, 0, 0, 1, 0, 0, 0, 1. So we have to go from each endpoint to another endpoint. So let's go 0, 0, 1 to 0, 1, 0. So then R1 of t, 1 minus t times x unit plus t times y unit, or x unit minus t x unit plus t y unit. If we take the differentiate this with respect to t, we have minus x unit plus y unit. When t is equal to 0, we have x unit, and when t is equal to 1, we have y unit, because 1 minus 1 is 0 for x unit. So then we could do f dot dr. How did I get yellow? So we have y x unit plus z y unit plus x z unit. We said x was 1 minus t and y was t. So that leaves us with t x unit, and z is going to be 0 plus 0 y unit plus 1 minus t z unit. And then we're going to dot that with the dr, which was minus x unit plus y unit, and that gives us minus t x unit. Well, not x unit, just minus t. Technically, we could do the z also, but because we have 0 z unit here, 0 times 1 minus t would be 0. So then we integrate f dot dr, so this goes 0 to 1, minus t dt. This is minus t squared over 2, or minus 1/2. Now we have to do our second path, so now we're going to go from 0, 1, 0 to 0, 0, 1, and we call this R2 of t. So now we're going to do 1 minus t for y, and then t for z. When t is equal to 0, we have y unit, t is equal to 1, z unit, simple. So we take the derivative, minus y unit plus z unit, and we say x is equal to 0, y was 1 minus t, and z is t. So now we rewrite f, 1 minus t x unit plus t y unit plus 0 z unit, and then dot that with dot dr. So dot these two together, and we're going to get minus t minus y unit dot ty unit, and that's just t. So then we're going to take the integral from 0 to 1. Sorry, negative t dt. Just as before, it's negative 1/2. And then the next thing to do would be to go on the third path. So far we have 1/2 and negative 1/2, negative 1/2 and negative 1/2. Now the final thing would be to go from, we went from 1 0 0 to 0 1 0. Then we went 0 1 0 to 0 0 1. Now we're going to go back 0 0 1 to 1 0 0. So R3 of t is going to be t x unit plus t 1 minus t z unit. T is equal to 0, we get z unit, t is equal to 1, x unit, which is what we're trying to do because that matches our points. So then we can take the derivative of R3. So this would be just x unit minus z unit, and then we're going to dot that with f. Remember, so f for this one, x is equal to t, y is equal to 0, z is t 1 minus t. So f then is going to be 1 minus t y unit plus t z unit, and we're going to dot that with our dr3 of t, and that just gives us minus t again, or f dot dr is equal to minus t. And then we integrate from 0 to 1 minus t dt, and that's minus 1/2. So we have minus 1/2 plus minus 1/2 plus minus 1/2, or minus 3/2. We can also take the curl of the function. So take the curl of f. Remember, f was y x unit plus z y unit plus x z unit. We can then make a 3x3 matrix. Partial x, partial y, partial z, y, z, x. Okay, so this is the curl of f written out. So when we take this, we're going to get minus z unit, or not minus z unit, minus z x unit, then we're going to have minus y unit times x plus z unit times minus y. So the curl of f is just going to be minus z x unit minus y unit x minus y z unit. Sorry, no unit there. I forgot. We are taking derivatives, so it should actually just be minus x unit minus y unit minus z unit, and this gives us the vector -1, -1, -1. And for our surface, we said x plus y plus z is equal to 1, or z is equal to 1 minus x minus y. So then when we parameterize, we're going to say our u of v is going to be u x unit plus v y unit plus 1 minus u minus v z unit. We're going to say u is equal to x and v is equal to y. So then z is 1 minus u minus v. It looks like we didn't really do much, but we're going to say 0, v is greater than 0, but less than or equal to 1 minus u. And then we take our partial derivatives of r, partial u is going to be x unit minus z unit, partial r, partial v, y unit minus z unit. And this looks eerily familiar to something else we've done before. So I'm just going to write x unit, y unit, z unit. Then we're going to cross these two terms. So ru cross rv, and then that's 0, 1, 0, -1, 0, 1, -1. And when you do this all, it's x unit plus y unit plus z unit, or 1, 1, 1. And we could take the magnitude of this, which will be square root of 3, very simply. And then we integrate over the surface the curl of f dot ds, or so then we compute it, it's still the curl dotted with ru cross rv du dv. And we're going to be integrating over the domain. So del cross f was -1, -1, -1. Ru cross rv was 1, 1, 1. And then we have to remember that we had our root 3 over here, because we're going to be dividing by the magnitude, because it's really ru cross rv divided by the magnitude of that. I guess it is a little confusing right here, but there's no magnitude right there. Magnitude is on the denominator. Our ds term also has a magnitude ru cross rv du dv, our root 3 term. So we're going to have our root 3 du dv. Those terms are going to cancel. So when we set up our integral, we have -1, -1, -1 dotted with 1, 1, 1 du dv over the domain, which I will be doing right now. Well, the domain I said, remember when I said u right here? So we're going to have one of these go from 0 to 1 and the other one go from 0 to 1 minus u. So first take this dot product, -1 plus -1 times plus -1 is -3. And then when we set up our integral, let's do this, 0 to 1, 0 to 1 minus u, dv du, because we don't have any function in here anymore. So we're just integrating this now. So let's integrate with respect to v. So this is -3 times 0 to 1, and then we have v from 0 to 1 minus u du, and that is going to be -3 times 1 minus u integral from 0 to 1 du, -3 times -u minus u squared over 2. So -3 times, this is evaluated from 0 to 1, -1 minus 1/2 this should be a positive, because a negative times a negative is a positive. So we can distribute that in there. And 1 minus 1/2 is 1/2, and that's -3/2. So that's the basics of Stokes' theorem. You can take all three line integrals, or you can just take the curl of the function and dot that with the normal vector and do all this, and not so bad. Just got to go step by step. Thank you.